Hello, my name is Jared Walden, and I'm a master's student at the University of Tennessee. Today I will be presenting on packaging a top-cooled 650 volt, 150 amp gallium nitride power module with insulated thermal pads and a gate drive circuit. Other key members on this project include you, Ziwei, and Leon. My advisor on this project is Dr. Bai. Industrial members include General Motors, Hella, and GAN Systems. In this presentation, I will be providing a project overview and discuss the power module design. Then I will cover an electrical analysis of the module, and finally I will display the fabricated module and provide information on experimental testing. In this project, our goal is to develop a 650 volt, 150 amp flip chip GAN half bridge power module with electrical insulation and an integrated gate driver, while also incorporating a DBC substrate for heat dissipation. The proposed power module seeks to lower the thermal impedance and parasitics compared to present discrete designs. Also, applications for this power module can include onboard EV chargers and motor drive inverters. So for this design, one can see the half bridge setup with a positive DC link, a midpoint, and a negative DC link. Additionally, there are decoupling capacitors between the DC link terminals, as well as an integrated gate drive circuit shown here and here. Also, the power supply circuit is shown here next to control 1. And finally, the DBC is shown here, which is interfaced between the PCB and heatsink. The GAN dies are attached to the bottom of the PCB, and then the DBC is attached. This module includes GAN devices in parallel with each individual die rated for 650 volts and 150 amps. The PCB layout aims for symmetric gate loop designs for parallel devices and flux cancellation for the power loop. In ANSYS Q3D, the gate drive and power loop parasitic inductances are calculated. The gate loop parasitic inductance is 7.88 nanohenries, and the total power loop parasitic inductance is 0.77 nanohenries. We can then extract those results and implement them into an LT-SPICE simulation with the provided GAN systems model. For the fabricated PCB, all gate drivers and power supply are integrated into the smart PCB. The GAN switches are triggered at positive 7 volts and negative 5 volts, with an input power supply that can accommodate between 6 to 16 volts. Additionally, all of these components are automotive qualified. Shown here is the top view and bottom view of the PCB. Its dimensions are 3.37 centimeters by 4.56 centimeters. The bottom view provides a good look into the GAN dies on the PCB, shown here, 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 and here. In the lower figure, one can see the populated PCB and the attached DBC. And now to the power module testing. The top figure shows 3 power modules next to a quarter and a ruler, just to provide a better idea of the size of the power module. The bottom figures display our test setup with additional bulk capacitors attached to the positive and negative DC links, as well as copper connections to the positive DC link, midpoint, and negative DC link. A double pulse test was set up at 450 volts and 150 amps. Figure A displays the test waveform with a long first pulse as the current through the inductor increases and a short second pulse. Figure B is the turn-on waveform where the approximate turn-on time is 40 nanoseconds, and Figure C shows the turn-off waveform. The approximate turn-off time is 20 nanoseconds. To summarize our progress so far, we have successfully integrated the gate driver, decoupling capacitors, and the DBC onto the fabricated PCB and tested it at switching frequencies greater than 100 kilohertz. In the near future, we plan on finalizing the thermal characteristics of the device and complete the mechanical assembly of the GAN power module. That concludes my presentation, and thank you for listening.